Hi, welcome back. Last time we met, we spent some time talking about the various receptors and the natural ligands for those various opioid receptors in the body. There's things called dynorphins, there's things called enkephalins, there's things called endorphins, metenkephalin, leuenkephalin, and so on. And we said that there was a conserved sequence in those particular peptide molecules, that tyrosine, glycine, glycine, phenylalanine moiety. All right. I showed you and asked you to contribute your thoughts on how that tetrapeptide might bind a particular receptor, what available interactions there would be. And you guys did good, right? Okay, so then we talked about the receptors, and we said that they're G protein coupled receptors, and we said that those G protein coupled receptors were coupled to an alpha inhibitory subunit, but we also have a beta gamma subunit as well. All right. We did make mention of the fact that these G protein coupled receptors are seven membrane passing domain receptors. They have this extracellular domain, classically referred to as the address, so to say. And when something like morphine binds, morphine will change the conformation of the receptor, and then that will allow for the trimer, the alpha, beta, gamma trimer to become active, right? The alpha subunit is inhibitory, so that decreases cyclic AMP, and then all the downstream effects that are typically associated with cyclic AMP production are suppressed. And again, you got to keep in mind your nervous system has a basal rate. It's firing at a constant rate for sensation and perception and nociception. And as such, these receptors are always, excuse me, the adenylyl cyclase is always making some level of cyclic AMP, but when you remove it, it has an effect. What else do we note? We note the presence of certain channels. Right? First and foremost, how about some calcium channels? All right, so here's a calcium channel. Here's a calcium channel presynaptically, let's say. The beta gamma subunit of the trimer can actually modulate the effects of these calcium channels. In fact, it can close them up, shut them down. And if you block calcium channels, you are not achieving the adequate calcium concentration presynaptically that's going to allow these vesicles to be transported to the presynaptic terminal, merge with the terminal, and then release, say, glutamate. If glutamate isn't released, then there is decreased or little to no neurotransmission. No glutamate, no neurotransmission. Okay. What if we have postsynaptic opioid receptors that bind morphine? Still going to have your alpha, beta, gamma, but this time around, maybe we have potassium channels. And if those potassium, I don't know how that happened. I'm so sorry, but I'm just as frustrated now as you. I have to figure out a different way to do this. But if the beta gamma subunit come over here and over here and open up potassium channels, potassium is going to leak out. And as potassium leaves, secondary to potassium channel opening, the membrane potential is going to get more and more and more negative. We are going to hyperpolarize that postsynaptic membrane. And it's going to be very difficult then for an action potential to get generated and propagate to send a pain transmission or a pain signal. Okay? All right, so all of that is secondary to morphine binding to an opioid receptor. Now, we made mention of the fact that morphine is the prototype. And I already told you about how tyrosine, glycine, phenylalanine binds to the opioid receptors. Compare the structure of that tetrapeptide to that of morphine. What do you see that resembles that tetrapeptide in morphine? Well, this is very tyrosine-like, isn't it? If you look at just this area of the molecule, right, that's essentially a phenolic group. And then there's one, two carbons that are spaced out between the phenolic group and then this amine. So it's reasonable to think that that area I just encircled represents or mimics tyrosine. Okay. This area here, of course, is going to be that N-terminal group, the alpha amino group in tyrosine on the tetrapeptide. All right. And then despite the fact that there is an alcohol here at the sixth position in morphine, this could start to resemble a phenylalanine-like appearance as well. Okay, it's not aromatic, it is unsaturated. There's a double bond between the 7 and the 8 position, yes, but again, too, um, it's not phenylalanine, but it's phenylalanine-like, we'll say. All right. Considering all of that, I would predict some H bonding interactions with that 3 position. I would predict ionic interactions with that tertiary amine that's going to be positively charged at physiological pH. And I would also predict some H bonding here with that alcohol at the 6th position. But let's not rule out the potential for hydrophobic interactions at that 7 and 8 position. Okay? All right, so let's move forward and see what we can figure out here. The classical description of the opioid receptors used to utilize a site, a type of site binding. So we had the T site and then the P site. The T site was mostly for the tyrosine binding, and then the P site was for the phenylalanine binding. So we had T site binders and P site binders. And when you start to tease out what the crystal structures have revealed about opioid agonists binding to the mu receptor, we can say that morphine is typically regarded as a T site binder, and the 3 prime, or excuse me, the alcohol at the 3 position is going to H bond here. Here is that anionic center that we talked about. And then we have a lot of real estate up here for additional interactions. Okay. I'm drawing the molecule like this as such in two dimensions, but in reality, it's probably being pulled down like this such that the positive charge is more downward facing, so it can interact with that aspartic acid residue. And there is a lot of surface area. There's a lot of real estate in the ligand binding domain of the opioid receptors. Remember, the natural ligands are these peptides, pretty large molecules. So morphine is a small molecule relative to a tetrapeptide. And because of that, we have a lot of unexplored space in the ligand binding domain. Nonetheless, as we expected, here's the positive charge, and then there's an aspartic acid residue forming that ionic interaction. Here is a tyrosine residue in the ligand binding domain. And guess what? That is going to H bond with the alcohol at the 3 position. And then the crystal structures have revealed the presence of water molecules that are coordinating between the alcohol at the 3 position and then a histidine residue in the opioid receptor. Right? And then there are additional hydrogen binding interactions between another tyrosyl residue and then the alcohol at the 6 position. Okay, so when you look at the sum of these interactions, what you end up with then is a potent agonist. It has high affinity, but it also has high intrinsic activity. Okay, so morphine binds well and it activates well. From a structure activity perspective, I can tell you there is no shortage of analogs that have been synthesized over the years. A scientist named Philip Portuguese, he's retired now, but he spent his career studying opioid receptors and opioid receptor agonists, and he's got a wealth of literature that he has produced out of his lab over the decades. But since morphine is the prototype, everything gets compared to morphine. Even when you calculate morphine equivalents and trying to convert morphine equivalents, you're going to do your calculations based on morphine. So let's go ahead and just look at the structure of morphine, uh, point out what's important, which I think you already know, and then we can start talking about what happens when we change certain aspects of morphine and what we end up with. Right. And I guess I'll start at the 3 position right quick. At the 3 position in morphine, we have an alcohol, an OH group, and it turns out that from a binding and intrinsic activity perspective, you're going to do best with an alcohol at the 3 positions. So your R1 group here is best when it's an alcohol. All right. When you start to consider derivatives of morphine, specifically something like codeine or heroin, all right? Remember, in heroin, it's an ester. In codeine, it's a methyl ether. And when you take those molecules and try and fit them into the opioid receptor, now they may bind, but they're not going to activate very well. However, metabolism can come into play and convert the alcohol at the 3 position from this methyl ether into the desired alcohol. And likewise, we already mentioned that the ester in heroin can get hydrolyzed and form the alcohol that lends to high affinity binding. Okay, so we do best when we leave R1 as an alcohol. These phenanthrene derivatives, we leave them as is. There's that ethereal bridge at the 5 position here. And then we get to the R2 position. This is the 6th position on the ring system. And again, too, not surprising. based on what I showed you on the previous screen, activity is going to be best when that R2 group is an alcohol. All right, so you could substitute that alcohol with a different derivative, a different isoster, if you will, and see what happens. And it turns out that you have good activity with an alcohol, but if you were to take that alcohol and oxidize it to a ketone, all right, you get some activity, but that activity actually increases then if you also reduce the double bond. Okay, so let's say that again. Activity at the R2 position is very good when it's an alcohol, but if you take it from an alcohol to the carbonyl group and you also reduce the double bond, you actually make a molecule that is almost 10 times as potent as morphine, right? And that's what we see with a drug called hydromorphone or dilaudid, right? So hydromorphone or dilaudid is an oxidized slash reduced analog of morphine, oxidized at the sixth position, reduced between the seven and eight position, right? And then there isn't too many other things to say with regard to the sixth position. I'm going to shift over to this green area here. This is the 14 position. Right? Now in morphine, we don't have anything substituted at the 14 position. But what was discovered is that if you oxidize the 14 position and have an alcohol there, it can actually increase activity again, more so. And when you oxidize the 14 position, what you end up with is oxycodone and oxymorphone derivatives. These are actually theoretically more potent. Okay. Then lastly, what about the northern area of these molecules? Is there anything interesting or important to say about what's going on topside? And with regard to the R3 position, turns out that that methyl group is probably optimized as is, because when you start to make homologs such that you have an ethyl or a propyl or a butyl substituent, you actually decrease activity. And then when you introduce cyclic alkyl groups or even an allylic group, what you end up producing is not agonists, but rather antagonists. All right. So if you were to put a cyclobutyl group or a cyclopropyl group or an allylic group, coming off the nitrogen instead of a methyl group, you convert that agonist into an antagonist. And I can tell you that the scientists who made those derivatives weren't necessarily trying to synthesize an antagonist, but what a wonderful discovery that ended up being. Okay. Now, metabolically speaking, let's pause here. And when we come back, I'll tell you how morphine gets metabolized. Give me a minute.